I want to walk through a few concepts that are in Chapter 8 for right now in your the Whit and Whit book. And the chapter is entitled Population Samples and Probabilities. We've talked about all those a little bit. We've talked about the difference between population samples. We've talked a little bit about sample procedure. Say a little bit more about that now. We've talked a little bit about probability in terms of, for example, p-values. P-values are probability values. I want to say a few more kind of basic things about those. I would first make the point that we probably probably make most of our decisions in life based on probability. When you get in your car to drive somewhere, do you know for certain, without a shadow of a doubt, you're going to get there safely and in one piece without an accident? And you don't, because that's happened to probably all of us where we've not always gotten there as we planned. But we figure that we probably are. And most of us don't say, well, I don't think I'll go out today because someone might run into me. Well, that may be true, but we generally make the decision in spite of that possibility because we consider it such a slim possibility that it's not going to stop us from whatever we were going to do. Much like, the p-values I referred to. If something is likely significant, if we have a less than 5% chance of being wrong saying that, we're okay with that. But now, probabilities kind of vary with the situation. For example, let's go back to getting our car again and make another trip. If there's a 99% probability you're going to get where you're going okay, is that a reasonable probability? Is that enough for you to go ahead? Yeah, I think I'll take that drive. 99%. I see in odds. Some of you playing the home version of the game, weigh in. Yes or no? Is that going to be enough for you? 99% chance you're okay. Yes, sure, yes. Anybody want to take exception? Not yet? 99% sounds pretty good, doesn't it? Hey, if you make 99 on every test, you're a genius. Probably, unless you're a real good guess or BS or whatever. But so 99 sounds pretty good. So nobody's willing to say that 99% isn't good enough for you, except me. Okay, let's do some math, as I am prone to do. Yeah, good point. 50-50. That may be enough to do it. Let's do the math. Let's say you go to work 200 days a year. And you drive there and you drive back. That's 400 trips just driving to work. Somebody's making a good point. Actually, I can make it even stronger than that. So you make 400 trips a year. Oh, and you probably go somewhere during the weekends. Probably make a couple of trips. Let's say conservatively, you get in your car and go somewhere 500 times a year. If you were successful 99% of the time, you had 5 accidents last year. Now, some of you may have. I don't know. I doubt it. I doubt most of us are willing to say, okay, I'm going to drive, so I'm probably going to have 5 accidents next year. In that case, 99% isn't nearly high enough if you think of what the math would be. So 99% sounds good, but it's not good at all because you're going to have a bunch of wrecks every year if that's your case. Now, if you were to go as you were going through school and you were assured of making 99 on every assignment, like I said, yeah, we'd take that in a second, wouldn't we? The issue is that we have different contexts. Let's say the amount of time, 5 minutes. 5 minutes isn't very long to drive to work, but it's a long time to hold your breath. So is 5 minutes long or not? And the answer is it depends. So what probability is acceptable, or whether a probability is acceptable, the answer is it depends. 99% isn't good enough if I'm driving my car. But you know, what if I've got somebody said something was 50-50 a second ago. What if I've got some dread, terrible, awful, likely fatal disease that most people just die from? Can I be any more morbid than that? Probably not. But I found this doctor who treats people with my condition, and he's got a 50% survival rate. Hey, all of a sudden, 50% sounds pretty good to me. So is 50% good or not? Well, it's pretty good in that context. It may not be good in other contexts. So the answer as to what an acceptable probability level is that it depends. When the stakes are real high, like having an accident, you want to be pretty sure. When your present circumstances are pretty low, you'll take whatever you can grasp at. So it depends what an acceptable probability level is. Come back to that in a minute. Let me just walk with me, as I say, through Chapter 8 on a couple of things. We've already defined sample and population. I'll do it again. Population is everybody you're talking about. The sample is who you get your data from. And the example I used earlier was if you're wanting to know something about all third graders, you can't get information from all third graders. You take a sample of it. Now, there's a section on, a little subsection I'm going to pay kind of close attention to on page 175, about a third of the way down the page. It says optimal sample size. The question is, how big does your sample need to be? The answer is, it depends. Depends on a lot of things. It depends. Well, actually, they say it very well. They say there is no simple rule of thumb for determining the best or optimal sample size for any particular situation. Oftentimes, samples in the hundreds or even thousands, the hundreds of thousands for surveys, but there are less than 100 for a lot of experiments. Here's the reason. Here's the reason. It depends on your, one of the reasons it depends is on your research design. You often, I think, have used the term random sample or randomized sample. What a random sample means is that, first of all, to select your sample, everyone in the population has an equal chance of being selected. And the second part of randomness is random assignment. If I am picking two groups to compare, say one with who's taught method A and one who's taught method B, everybody also has the same chance of being in one group or the other. That's an experimental study. Most of our research in the social sciences is not true experimental research. It is quasi-experimental at best. Quasi-experimental is different than experimental in that you don't have the randomness in quasi-experimental research. And the reason you don't is because you can't. I cannot randomly select a couple hundred third graders from the country and have them and put them into two groups, teach them one way, one group one way, teach the other group the other way. I can't do that. They're already in classes. They're already being taught a certain way. So I cannot randomly select, or randomly assign that sample. If you can randomly select and assign, your groups don't have to be very big. If you can, and you're looking at intact groups already, that you lose a little in that you typically have to have larger sample size. And there are some there are a lot of formulas to look at sample size or what the optimal sample size is. There are a couple of free downloads you can look at. One is called something like G3 power or something like that. And there are a lot of complicated formulas that tell you can figure out, what somebody thinks you need as a sample size, but it's kind of fuzzy. I will say that, back to this idea of significance and probability, that if there is something significant going on, the larger the sample size, the more likely you're going to determine that significance, generally to a point. After you get past a group size of about 30 or so, and you'll see this when we use some of the charts in the back, you'll see some things kind of level out. After you get past about 30 or so, your statistic has to, it doesn't make much difference in terms of whether you can find significance or not. But sample size in itself is not, there's nothing magic about that. There was a, I meant to look this up. There was a study years and years and years ago, and in which it was a political election year, and we're voting for president, Republican and Democrat. And so they did a telephone poll, called up a bunch of people. It's like called up, I don't know, like, I want to say 2 million people. It was supposedly the largest sample size ever for anything. Well, gee, that's got to be good information, right? Well, the results came across that the Republican guys got it nailed down. The Democrat doesn't have a chance. Guess what happened? The Democrat wiped the floor with the guy. Now, I slipped in something a minute ago. It's kind of subtle. Can you think of a reason of something about what I just said that would be indicative of why the results with a huge, huge, huge sample size were so misleading in this particular case? Well, we call random numbers. The suggestion was it wasn't random. Question that maybe how the questions work. No, the questions were worded fairly. The idea was they pulled them from certain college. There it is. It's where they pulled them from, but not long. Who had access to the phones? I said this was a long time ago, back before everyone had a phone. I want to say this was maybe 44, 48 or something like that. The Republicans had the phones. So, of course, you're going to get a result in favor of the Republicans. It was all over the country. So, but they called them on the phone. They ended up calling the Republicans. Who's going to win? Well, the Republicans are going to win because those are typically the people they asked. So the sample selection is much more important than the sample size. That's my point. There are different kinds of sampling. What I described is just, well, not this telephone study, but the idea of total random. See, well, it really wasn't totally random because not everybody in the country had an equal chance of being selected. Only the people with telephones. But if everybody in the population has an equal chance of being selected, and we can truly, purely randomly, just figuratively, maybe it used to be literally, put all the names in the hat, draw out names, or actually, of course, we have the computer do that now, and you can really, truly randomize things. That's one thing. But a lot of times you want to do something else. Let's say I want to know something about, you mentioned college a minute ago, I want to know something about our undergraduate college students. And I probably have a larger freshman class than a senior class. So I may want to make sure my sample is proportionally representative of the class. For example, let's say I had 30% of the college students were freshmen. I would want 30% of my sample to be freshmen. So in that case, it's called stratified sampling. It's perfectly legitimate because class status is an important factor or might be in this study. If it is, that's totally a legitimate thing to do. So that's not purely random either, but it's stratified. Couple bad ways to sample, although sometimes you have to. Something called convenience sampling. Convenience sampling means, hey, you get who you can get. Sometimes you have to do that, but you have to acknowledge a weakness in that study design. Sometimes convenience sampling is by nature biased. Let's say, for example, I go to Applebee's and I randomly interview people leaving Applebee's, and my question is, hey, how do you like Applebee's? Well, I bet they're going to like it because they chose to eat there. So you can't say that that's really an unbiased sample. So there's such a thing called sample bias. A really good example of sample bias is you see, sometimes the news is bad about this, but other TV kinds of things and radio kind of things are maybe even worse. What do you think about such and such? Call this number and tell us. You vote yes, no, or whatever. It's like American Idol. I don't know. Are you for or against this issue? Well, a lot of times the issue itself helps people decide whether they're going to call or not. So it's very possible, likely in some cases, maybe most cases, I don't know, that the question itself, somebody said something about the wording of the question. The wording of the question, or not just the wording, but what the topic is going to influence who participates and therefore what kind of data you get. So in a word, these call-in polls aren't worth the paper they're not written on. Because, again, not so much the sample size, but the sample selection. Some good examples are, let's say I'm flipping a coin. Let me get what I want on here. We talked about randomness. Good example of randomness is flipping a coin. Oh, good. There we go. When you flip a coin, one of two things can happen. It can come up heads, it can come up tails. So what's the probability of flipping a coin and getting a head? And I'll write it this way. The probability of getting a head is how much? Okay, this is not rocket surgery. Mm, 50 what? Okay, 50%. Okay, all right, one half. Okay, and we can. You're right. We can say it either way. We can say one half, or we can say 50%, or we can say 0.5. So they all mean the same thing mathematically. So you've got a 50% chance of getting ahead on one flip. What if we add a second coin or a second flip? If we do that, how many possibilities of two flips are there? Okay. 4 is correct because you can get a head and a head, a head and a tail and a head, or a tail and a tail. And those are the only 4 ways you can have two flips, either flips of two coins or two flips of the same coin. So, what's the probability? Well, each of these four possibilities is equally likely to happen. So, what is the probability of getting two heads? Probability of getting two heads is there are 4 of them. Only one of those is two heads, so that's 1 out of 4, and you said or 25%, which is also correct. So 1/4 or 25%. That's one way of figuring it out. We'll talk about another way in a minute. What's the probability of getting the same result on two flips? The probability of getting the same result on two flips. And again, you can look at the list again. Out of these 4 equally likely outcomes, which ones give you the same result for the first or the second? This one does. And this one does. So that's 2 out of the 4, or 50%. So you've got a 50% chance of getting the same result. Likewise, what is your chance of getting different results? One of each, one head and one tail. If the order doesn't matter, just one of each is going to also be the other 50%. Now, there are a couple of things. I want to make sure I don't skip over. Two ways of things I want to look at. First of all, the definition of probability, and I hadn't really defined it, so I guess I need to. Page 181. The probability refers to the proportion or fraction, that we've done it both ways, percents and fractions, that a particular event is likely to occur. The last percent we talked about was the event getting the same results. There are a couple possibilities I want to look at here. Let's see if I can leave my example up. Even though I'm erasing these numbers, I'm gonna ask the same question, one of the same questions at least, and look at it a different way. So remember the answer, please. Okay, there are a couple of keywords I want to talk about. And the keywords, if you've ever had a logic course or something like that, you see a lot of times the keywords are and. The other one is or. Now, we call these, we further categorize these and say the and has to do with the multiplication rule. The or has to do with the addition rule. The last question I asked about what's the probability of getting the same results? No, let me skip ahead. Let me get back to the one before that. What's the probability of getting 2 heads? Another way of looking at this question is what's the probability of getting a head and another head? Now, I've already classified the and to go with multiplication. Here's why. When you're taking the probability of 2 things, there are 2 probabilities you've got to put together, either with multiplication or addition. Here's why it's an and. What's the probability of getting a first head? So what's the first probability of getting a head? You flip a coin one time. Just one time. Just probability of flipping a coin and getting a head. First flip. Okay. I'm going to say it's 1/2. You're saying 50%. That's fine. So 1/2. Okay, you flip that coin. You get a head. What's the probability if you've flipped the coin the second time, either the second coin or the second flip of the same coin, and getting a head? So what's the probability of here? 1/2. We said and goes with multiplication, so 1/2 times 1/2 is 1/4. And we said when we were listing things and identifying the cases, that's 1 out of 4. So you get the 1/4 the same way. Let me change my scenario just a little bit. Let's say we're rolling a single die. What's the probability, so I don't need these, of getting a 1 or, oops, or a 2? And there are two ways we can figure this out. I want to make it simple so we'll see both of the same thing. What's the probability of rolling a die and getting a 1? 1, 6. 6 sides, one of them is a 1. So 1 out of 6 is the probability of getting that 1. What's the probability of getting a 2? 1/6. What's the probability of getting a 1 or a 2? That's an or, so we're going to add 2/6 or 1/3. Now, when I roll a die, I can get either a 1, a 2, a 3, a 4, a 5, or a 6. There are 6 possible outcomes. These two are the ones we're talking about. That's 2 out of 6, or 1/3. So the key thing is, when you get to probability of two things, if the key word between them is and, we multiply. If the key word between them is or, we add. I could ask, for example, what's the probability, and I will. Let's move to the page. What's the probability of getting a red queen when you're drawing from a deck of cards? Isn't that the same thing as getting a red and a queen? Is that right? A red and a queen? Yeah, you're right, for one of two reasons. What's the probability of getting a red? 1 out of 2, because half are red, half are black. So 1 out of 2. What's the probability of getting a queen? There are 4 queens in the deck. 4 out of 52. And we said it's and, so we multiply. Do 2. I'm going to reduce my fraction to 1 out of 26. Which is also the same thing as 2 out of 52. There are 2 red queens in a deck of 52, so that reduces to 1 out of 26. Again, we multiply the probability. What's the probability of getting? Hang on. Oh, I had a bigger one of these. I do. What's the probability of getting a red or a queen? Not a red queen, meaning red and queen. Sometimes when you don't see a keyword like and or, sometimes and is kind of included or implied. If I say red queen, it's got to be both. Both is a synonym for and as well. So the probability for getting either a red or a queen, what's the probability of getting a red? 1 out of 52. The probability of getting a queen is 4 out of 52. Or means we add. I'm sorry, whoops. You'll catch me on these things. The probability of getting a red is 1 out of 2. Yeah, sorry. I told you, it's not when I mess up, not if I mess up, but when I mess up. Okay, so the probability of getting a red is 1 out of 2. The probability of getting a queen is 4 out of 52. Well, if I look at 1 out of 2, normally we reduce fractions, but I'm going to expand them. 26 out of 52 cards are red, plus 4 are queens. So that's going to be 30 over 52, whatever that reduces to. Yep, some of you are ahead of me, yeah. So either a red or a queen. Chances are A little better than half. Well, half, it's going to be better than half because your chances of just getting a red are half, plus you've got chances of getting success another way too, so it's going to be more than half. Walk through with me a couple of things in the textbook. Let me just close this out. I don't want to close it out like that. Okay. Walk through me within the textbook a couple of things on first of all, page 183, progress check 8.6. I'm just going to kind of talk through these real quickly. And the question is, you're equally likely to be born during any of the months. What's the probability of Jack being born in June? June is 1 out of 12 months. If chances are equal, 1 out of 12. Hey, what's the probability of Jill being born in June? The same thing. It doesn't matter. Okay, the chances. And I say that facetiously, but there's also sometimes our intuition can mislead us. You're right. Counting the days, but we specify that the chances are equal. We already said that, even though you're right, they're not exactly, because some months are longer than others. Yes, chance of being born in June is a little better than chance of being born in February, but forget important details like that. Anyway, back to my sometimes intuition misleading us. Let's go back to that flipping a coin again. All right? And I don't dismiss your comment because you are absolutely right. That would change the probability a little bit. Let's go back to flipping a coin. I flip a coin 9 times and I get head every time. Head. How many ever that is close to 9? What's the probability of me getting a head on the 10th flip of the coin? How much? It's 1/2 or 0.5, like you both said. Yeah, that's because those events are independent of each other. They're not. One does not depend on another. I think of things like this. If you're a sports fan, if you go to, it's basketball season, let's say, and we go to a basketball game, and a person is shooting 2 free throws. And he is an 80% free throw shooter. What's the chance of him getting both free throws? Both. He's got to hit the first one, and he's got to hit the second one. So how do I figure it out? What's his chance of getting the first one? 80%. 0.8. What's his chance of getting the second one? 0.8. So what's his chance of getting both of them? 0.64. 64%. There's a 64% chance he's going to hit both of them. Now, I would argue a little bit. I guess this is kind of nitpicky, like your days of the month is, but so you started, I'm going to follow up with it in the same kind of comment. I would argue a little bit that these are not totally, purely independent events. Because if I'm shooting free throws and I miss the first one, let's say, I can make an adjustment for the second one. So there's a little wiggle room in that. But you get the idea that, okay, guy's shooting 80% good, he's going to can both of these. Well, there's less than a 2/3 chance he's going to can both of them. What if he just needs one free throw? I just need one free throw to put the game away. So I want to hit, I'm shooting 2, I want to hit the first one or the second one. What's his chance of hitting the first one? 0.8. Chance of hitting the second one is 0.8. Hang on, I'm saying something wrong here. Oh, I know what I need to do. Let me ask this. I asked the wrong question. What's the chance of missing both? I left out a step. That's what was wrong with it. What's the chance of missing both? What's the chance of missing the first one? Not hitting it. 20%. 0.2. What's the chance of him missing the second one? 0.2. So what's the chance of him missing both of them? 0.04, right? So he's got a 64% chance of hitting both of them. He's got a 4% chance of missing both of them. What's the chance of him hitting one of them? Or at least one of them? We just need to make one. Ah, there you go. If the chance of him missing both is 4%, the rest of it must mean that he's going to hit something. So, sometimes, again, as we said, sometimes you take what you've got and you throw away what you don't want. Well, this is what we don't want to happen, the 0.04. So 1 minus 0.04, there's a 96% chance he's going to hit one of them. That will make more sense to some of you than others, but you can, again, we're combining probability of independent events, even though you got my little disclaimer about free throws being totally independent. But we need a point to seal the game. My guy's an 80% free throw chance, a free throw shooter. 96% chance he's gonna hit something. What if he misses the first one? Then what's the chance of him hitting a second one? Is still 0.8 or 80%, yeah. He's got to hit something. Well, gee, good way to go, fella. You missed the first one. Well, there's still an 80% chance he's going to hit the second one. Although, again, there's some other things come into play where you might get a little rattled. Gee, the pressure's really on now. So there's some other nuances to that. But in general, that's the way the probability works. And you can put this together. Again, sticking with the sports theme for a second. Sometimes I think about in baseball when you get a runner on first and you sacrifice an out to get him to second base. If you look at your hitters having an average of about a 300 batting, there's about a 50%, almost a 50% chance you're going to score somebody. That I figured that out, but you can kind of work this. So I would argue that probability has to do with real life, and we use probability all the time, even though we may not run the numbers. Walking through the rest of the stuff on page 183, I let that kind of ramble away from me, but I meant to get there. Any month other than June. If there's a 1 out of 12 chance of being born in June, what about a month other than June? Yeah, it's 11/12 because there are 11 months that aren't June out of 12 altogether. How about May or June? That's like our dice question a second ago. It is the same question. May or June is going to be 1/12 plus 1/12 or 2/12, which is going to be 1 out of 6 chance. Skip over a page and look on page 184. Walk with me through progress check 8.7. Hint. These are all multiplication problems. The husband being born let me clear this off. The husband being born during January and the wife being born during February. Chance of the husband being born in January is 1/12. Chance of the wife being born in February, or any other month for that matter, is 1/12. The chance of both these things happening, 1 out of 144. I could ask, I could ask the same question, having the same work. Say, what are the chances of two people being born in the same month? 1 out of 144. Which is what B asked you, both being born during December, 1 out of 144. Both being born in January, 1 out of 144. Both being born in August, 1 out of 144. C is a little bit like that last free throw example we gave. Both the husband and wife being born during spring. A couple ways to figure it out. I'm for the easiest one. What's the chance of the husband being born during spring, which we define as April or May? That's 2 months, 2/12. Also, the wife being born during that same period, 2/12. So both these things happening. 4 out of 144, which reduces to what, 2 out of 72, which reduces what, 1 out of 36. So both people being born within any 2-month period is going to be 1 out of 36. Got something you may find surprising. We're talking about how sometimes your intuition leads you differently. If you take 30 people in the same classroom or whatever, and you ask them the day and month they were born, not the year, but just, February 12th or whatever. Do you know what the probability that you'll find 2 people born the same day and month is, roughly? Some 2 people out of those 30. And so this is kind of a classic question. Some of you may have heard this before. Got 30 people. What are the chances of some 2 having the same birthday? Not year, but just day and month. Any idea? I've already set you up as a trick question, so you need to be scared, to be afraid of it. It's about, and I could show you the modeling behind this, but nobody wants that right now. There's about a 2/3 chance you're going to find 2 people with the same birthday out of 30 people, because there are a lot of combinations. Yeah, there are 365 different days you can have, but the number of the ways that you can pair 30 people together, which is actually kind of leads us into the next section, but there are a lot of combinations like that. So a lot of combinations can cover those 365 days. Because I can make these 2 and these 2 and these 2 and these 2 and these 2. I can do that a lot. And I could get into the permutations and combinations, but nobody wants that either, to see how many ways you can do that together. But there's a bunch. I'll just say one word about conditional probability, and that has to do with, I'll just say an example I've already used. While there's a, what do I say, a 64% chance that the free throw shooter is going to hit both of them. And then I said after that, I said, what if he's already missed one of them? Then what's his chance? And you said 80% correctly. Conditional means you already know something has or hasn't happened. So I just kind of say that as a way of defining conditional probability. Okay. Any other thoughts, questions, or yeah, it could be 366 days. That's actually 365.25 overall. So if you're going to get that. Gail says 366 days sometimes, which is true. I appreciate your attention to detail, all of us. So keep those things coming in, because again, not everything is purely the way we give it as an example. Like again, that shooting free throws is really not. They're really not independent. The months really aren't equal in probability, so those things are true. So it changes the numbers a little bit. Any other questions or comments or thoughts? All right, then. Thus endeth the gospel of probability.